So the most important thing is please vote today if you're over 18 and eligible to vote.
I'm not.
Yeah.
My birthday's in March. I did try to.
And then the second thing is the final schedule. So for this class, it's Thursday, 12/19 from 2 to 5. It's not really gonna, let's call it 2 to 4. It's definitely not gonna be a 3-hour test. I usually write those finals trying to make them about an hour and a half long, so 2 hours should be plenty for everybody. So this is the one that's in this room, S1328. But then the other option is the day before, so Wednesday, 12/18 from 11 a.m. to 1 p.m. That's right next door, 1326. And you can go to either one of these and you don't have to tell me ahead of time. You can make that decision the morning of or whatever. But if one of those works better for you, just go to that one. Okay? I don't think I gave any homework last time, right? Okay, so we're going back to circular motion.
When will we get the quizzes?
Let's see. By Thursday, maybe? Let me think. I'll do my best. Maybe not by Thursday, though. But then definitely by Tuesday. Okay, so a week from today. Exams and quizzes will be back a week from today. Okay, back to circular motion. So I gave a whole set of steps for problems. The one thing I said about sort of categorizing circular motion problems is circular motion problems are either tetherball problems, and I haven't even talked about what I mean by that. Or not tetherball problems. And we've talked about the general steps for the stuff that's not tetherball problems. It turns out for this one sort of specific set of things, there's a very easy, simple way to go about it. And so I'm going to talk about that specifically. But for everything else, we've talked about how to go about it. So I'm going to do 2 more examples before we do tetherball problems. And I'm just going to go through the steps that I gave you. So the first one is like a mass on a string swinging in a circle like that. And this is down in this picture. So that means gravity acts towards the bottom of the page. And let's say that the length of the string is 0.2 meters. And the mass is 0.06 kilograms, 60 grams. So that's the mass of like a metal pinball. And I want to do 3 calculations. So let's say, that's the point A, that's the point B, and that's the point C. Is that how I'm going to do it? No, I'm going to do it this other way. I'm going to do A here, then B, then C. Okay. And what we want to do is find the tension in the string when the ball is at A, B, and C. Okay. So there are a couple of things that are going to come into this. At A, the tangential acceleration, magnitude, is 9.81 down. This is true whichever way this ball is going, but let's think of it as going this way. So it's on the way up at that point, but the tangential acceleration will be down. And at B and C, the tangential acceleration magnitude is 0. And that just has to do with whether the ball is rising at that instant or dropping at that instant, its height. At B and C, we talked about this in lab. At those 2 locations, the height isn't changing at that instant, and so there's no tangential acceleration. Okay. Does anyone have a feel for what's going to happen here? Where would you imagine that the tension in the cable is going to be the smallest of these 3 points? Like, at what point of these 3 would you imagine the string is the least likely to break? You have a feel for that? B, that's right. Yep. So the tension is going to be lowest at B, and then it's going to be in the middle at A, and then the highest tension is going to be at C. Was anyone in here ever a gymnast? Well, male and female gymnasts both do bar, is, some kind of bar thing is one of the events. And what you see there is all the bad falls on the bars happen when you're at the lowest point of your swing, when that tension in your arms is the highest. That's when, so they wear these leather grip things on their hands. And if you have some funky grip on the bar, it's going to get exposed as you swing through the bottom. That's when you'll lose your grip and go flying off. It's actually pretty hilarious to watch, but it's sort of scary when it's you. Okay. So let's do this calculation first at the point A. And I'm going to try to just bring out the steps. I really recommend, as you do problems like this, just keep making yourself go through the steps as they're listed out. It's a good way to not forget any of the things you have to do. Okay, so the first thing we want to do is choose a view of this path where we can see that it looks like a circle. Well, that's the view that I have drawn here. That's not always the case, but in this case, we can just do it exactly as it's drawn. So there's the circular path. And I'm going to use the coordinate system orientation that you would imagine, like this. And the point, next you have to choose the point on the circular path to analyze. So that's the point that we're looking at. Okay. Next, we want to draw a velocity vector. So that's going to be tangent to the path in the direction of motion. So that's straight up. Then we want to draw a tangential acceleration. In this case, it says that the tangential acceleration is down. Also, if you know that it's slowing down, you could say that it's opposite the velocity. And then draw the centripetal acceleration. That's always right towards the center, so here's the centripetal acceleration. So now we have the directions of all of those three. We have to calculate the magnitude of the centripetal acceleration, and that is always v squared over r. Okay, so, oh, and I didn't give the speeds. We have to pretend I did. So at A, the speed is 5 meters per second. At B, the speed is 4.59 meters per second. And at C, the speed is 5.38 meters per second. So we can't do this problem if I hadn't given those. So at this point A, we have 5 squared. What's the radius of this circle? The string has a length of 0.2, and notice that that string length is the radius of this circle. And so this comes out to be a magnitude of 125 meters per second squared. Now that we know the magnitude, we can combine that with the direction. The centripetal acceleration is in the negative x direction. So the centripetal acceleration vector is negative 125, 0. The tangential acceleration, the magnitude is 9.81, so this is 0, negative 9.81. And now we can come up with the total acceleration. It's the sum of these two parts. And so it's negative 125 for x, negative 9.81 for y. Okay? I just said that it's down. So I already drew it in the negative y direction, but okay, so now we have the total acceleration. Yes?
Where did the 5 and 0.2 come from?
Okay, the 5 needed to be given. I forgot to say it at the start of the problem, but we have to pretend that I did say it. The 0.2 is because the string is 0.2 meters long, and if you think about the geometry, the radius of the circle is the length of the string. Okay, so now we can go to a free body diagram. There is a weight down. That is the mass times 9.81. So that's 0.5886 down. And then the only other place the surroundings contact this mass is at the string. And so that force is parallel to the string, away from the body. And I'll call that T. And we're trying to find the magnitude of that force T. Okay, so now I'll go to Newton's second law. We have the weight 0, negative 0.5886. T is in the negative x direction, so plus negative T0. And these add up to equal the mass times acceleration. The mass is 0.06 kilograms. The acceleration is what we got before. Okay, so the x equation says negative t is equal to 0.06 times negative 125. And so you get negative t is equal to negative 7.5. So t is equal to 7.5 newtons. Okay? So if that string can withstand 7.5 newtons, this will be able to continue on its circular path. If it can't, it'll break there. So now let's do the calculation at the point B at the top of the circle. Like we said, we expect the cable tension, the string tension to be a little bit lower at the top. And let's just go through the steps again. I think it's good practice to just, think it through all the way. So first we're going to draw the view where we can see the circular path. And then that's the point that we're looking at, trying to calculate. The velocity vector is tangent to the path in the direction of motion, so straight to the side. Do you remember what I said about the tangential acceleration at the top? 0, yep. The height isn't changing, so there's no tangential. There is centripetal. In any circular motion, there's centripetal acceleration, so that goes this way. And now we can calculate the magnitude of the centripetal acceleration. That is always v squared over r. V in this case is 4.59. The radius is still 0.2, so we get a centripetal acceleration magnitude of 105.38 meters per second squared. Now looking at the picture, that's in the negative y direction. So the centripetal acceleration is equal to 0, negative 105.38. The total acceleration is the sum of the tangential and the centripetal. This time the tangential is 0, so the total acceleration is just 0, negative 105.38. What's the next step? Yep, perfect. So now we're going to do a free body diagram of the mass. We have a weight down of 0.06 times 9.81, so that's 0.5886 newtons. And the only place the surroundings contact the boundary is the string. So we also have a string force parallel to the cable, away from the body, so that's also down. Remember, this is at the top of the path, so the string is, pointing from the center up.
Should we give the string a different name because it's not gonna have the same outcome?
I'm sort of thinking of this as a different problem, but yeah, that's a reasonable thought. So now, but I'm still going to keep doing it like this. But yes, you're right. It's going to be a different value than we had before. Okay, so the forces, we have 0, negative 0.5886 plus 0, negative t is equal to the mass times the acceleration vector. This time that's 0, negative 105.38. This time it's the y equation that gives us something useful. So negative 0.5886 minus t is equal to negative, if you multiply 0.06 times negative 105, you get negative 6.32. And solve for t, and you get that t is equal to 5.73 newtons. Okay, so we got on the side, we got that the cable tension is 7.5 newtons. At the top, we got that the tension in the string is 5.73 newtons. What we're expecting is now when we do the calculation at the bottom of this circle, we're going to get something bigger than 7.5 newtons. Okay, that's where it takes the highest tension. Yep.
Do you have to make also a vector like an arrow? Like, you know how we did like, 5.73?
Oh, on the answer?
Yeah.
So no, we don't. This t is just the variable that we're looking for. Then if we wanted to, sometimes I ask these questions as like, what's the force on the object by the string?
Yeah.
Then you could write that as like force on the mass by the string. And you would plug this t value into that vector. So this would be like 0, negative 5.73. And this is what you would put the thing over because that's a vector. But this t is just a number,
Okay.
and so you don't need it for that.
Okay.
Okay, so last one. Now we're doing the bottom of the circle. So again, we're going to draw a view where we can see the circular path. This time the point we care about is down here. The velocity is tangent to the path in the direction of motion. So straight this way. There's no tangential acceleration here because the speed is constant at that instant. There is a centripetal acceleration this way. The magnitude of the centripetal acceleration is v squared over r. And this time the speed is 5.38. And the radius again is 0.2. And so the magnitude of the centripetal acceleration is 144.62. And so as a vector, you can see the centripetal acceleration is in the positive y direction. So the centripetal acceleration is 0, positive 144.62. And since there's no tangential, this is also the total acceleration. And now we can draw a free body diagram. Okay, so there's a weight force down of 0.5886. What direction, when this is at the bottom of the path, what direction is the cable force? Up, right. Parallel to the cable, away from the body. Then Newton's second law says 0, negative 0.5886 plus 0t is equal to the mass times the acceleration, which was 0, positive 144.62. So in this one, again, the y is the important equation. So we have negative 0.5886 plus t is equal to I didn't write this step down, so it's 0.06 times 144.62. And so solve for t, and you get that t is equal to 9.27 newtons. So there are two things going on that make the tension higher at the bottom of the circle and lower as you get higher. One is that gravity, when you're at the bottom of the circle, gravity acts opposite the direction of the centripetal acceleration. So when you're at the top of the circle, gravity is helping you stay in the circular path. When you're at the bottom, gravity is fighting that. So the string has to fight against gravity instead of gravity helping the string. Okay? And then the second thing is that the object is going faster at the bottom, and faster always means more centripetal acceleration. Anybody have any questions about that one?
I can go first.
Yeah.
I was gonna say V will always be given to us.
Yeah, for now, V will always be given. We'll be able to calculate that in certain problems when we start talking about energy, but not yet. Yeah,
Can you scroll up to the top for a second?
how far?
All right, and then I'll zoom out a little bit.
Okay,
Thank you.
sure. Okay. Let's do another similar problem. So let's think about an object going like a Hot Wheels car or a motorcycle or whatever going through a loop-de-loop. And let's calculate how fast the thing needs to be going at the top of the loop in order to stay on the path. Okay? So we'll think of let's think of a toy car going this way. Okay. And the question we want to ask is how fast does the car need to be at the top of the loop so it doesn't fall? And instead of doing this with one specific number, let's treat this radius as an r, okay? And then we'll get an answer in terms of r. And then at the end, we can plug in different values and see how the radius of that loop affects the speed that's required, okay? I mean, what would you guess? A small, like, how, like, do you think the required speed is going to be bigger for a small loop or a large loop?
Wait, can you say that again?
So is this car going to have to go faster if this loop is big or if this loop is little?
It's big as a car.
Yeah, the bigger the loop is, the faster the car is going to have to go. Okay. But we'll just do it with that r as if we know what the number r is, and then at the end we'll just plug in some different values and see how the speed changes. Okay. And we're going to assume that at the top of the loop the speed is constant. So we're going to assume that the tangential acceleration is 0 at the top. Okay, so the first step is to choose a view where the path is a circle. And that's the view that's drawn. And then the point on the path that we care about is right at the top. The velocity is tangent to the path in the direction of motion. So the velocity is straight horizontal like that. There's no tangential acceleration, and the centripetal acceleration is toward the center, so down. And now the magnitude of the centripetal acceleration is v squared over r. Do we know what v is? No, we're trying to calculate that. So I'm just going to leave that as V, and hopefully we will, at the end, be able to calculate that. Do we know what R is? No, that's the thing we're going to plug in values of at the end. So all I can do now is just leave it in this form. Okay. There's no tangential acceleration, so this is the total acceleration. I didn't write it as a vector yet, sorry. So the centripetal acceleration vector, this is pointing in the negative y direction, so this is 0, negative v squared over r. And this is the total acceleration vector. And now we can go to a free body diagram. So here's the car. There is a weight down. I didn't give this a value. It's not going to matter, but well, let me just put this in as 9.81 times the mass of this car. Okay, and we're going to see that that cancels out, so that it turns out that the mass of this car just doesn't have any effect on the answer. Okay, we'd get the same answer if it was 100 pounds as if it was 1 ounce. Okay. And now go around the boundary looking for contact with the surroundings. Where is the only place that there's contact?
The wheels by the car.
Exactly, the wheels. That's a pushing force, so it's going to be perpendicular to the surface, toward the body, and I'll call that N. Okay. And so now we can go to Newton's second law. And we have this equation that says 0, negative 9.81 times the mass, plus 0, negative n, is equal to the mass of m times 0, negative v squared over r. We probably have never done a problem like this with as many variables in here instead of numbers as we have. But we're still going to be able to get useful stuff out of this in the end. Okay, so now this equation has to be true. Like, let's just go to the y equation. That's the only one that's useful. So negative 9.81 minus n is equal to negative m times v squared over r. Okay. And this equation has to be true for this car to keep going along that circular path. Okay? Well, what in here is required for this to be physically realistic? The answer is, as long as, so the track cannot pull up on the car's wheels, okay? All the track can do is push down. So if this n ends up being a negative number, then we know that that car would have fallen off of that circular path, okay? And so what we're going to do is set that n equals to 0. That's the cutoff between what's possible and what's not possible. Okay, so we're going to set this equal to 0, and then we're going to solve for this other stuff. And I guess I left the m off of this. That's important. So now we have this equation that says negative 9.81 times m is equal to negative m times v squared over r. We can multiply both sides by -1 to get rid of the negatives. We can divide both sides by m to get rid of the m's. That's how you know that the mass doesn't matter. We're going to get the same answers no matter what the mass is. And we get that v squared is equal to 9.81 times r. Okay? And so v is equal to plus or minus 3.1, hold on a sec. (3.13) times the square root of r. And we want the positive because it's a speed. Okay, so now let's plug in some values. And so first of all, what if it's what if the loop is like this, like a regular Hot Wheels car loop-to-loop? So let's say that this r is 0.1 meters. Then the required speed to make that loop is 0.99 meters per second. So it could make that loop at about a little over 2 miles an hour. Okay, it doesn't take very much. Okay, what if the radius of that loop is 1 mile? So that would be 1609 meters. Then the speed of this car would have to be 125.55 meters per second. So 280 miles an hour. Yeah.
I don't think they make Hot Wheels like that.
Yeah, it's true. Anyone have any questions about that? That's a harder problem than I'm going to make you guys do, but you can hopefully at least sort of follow the logic and see how that works. Okay, so the last thing we have to talk about in circular motion is tetherball problems. And tetherball problems are problems where first, the only contact between the object and its surroundings is a cable. And second, the circular path is parallel to the ground. So what we're talking about is an object that's attached to something up there, attached to a cable, and moving in a circular path like that. okay, where this is down. So here are two cases that seem similar to tetherball problems but are not. The first one is so here are two that aren't tetherball problems. The first one of the first example problems we did was like this, where you have a ball connected to a string and it's moving along a circular path on a surface. Okay, so this one is, rolling or sliding. Along a surface. Well, this one, so this is not a tetherball problem because you do have the circular path parallel to the ground, but you don't meet the criterion that the only contact is the cable because this thing is also in contact with the ground, so there's a normal force. Are you with me on that? And then the other one is the example we just did. Where down is this way. So in this case, the only contact is with a cable, so that part is good, but this circular path isn't parallel to the ground. So that one doesn't count either as a tetherball problem. And we're going to use a different approach for these problems just because there happens to be a really simple way to approach them. One thing that is important, like this simple approach wouldn't be possible if this wasn't true. Tetherball problems are always uniform circular motion. And so remember, uniform circular motion means the speed is constant, and so that means that the tangential acceleration is 0. Okay, so here's a set of general steps for tetherball problems. And the first step is kind of the big one. It's the big difference between this approach and what we use for every other circular motion problem. Instead of taking a view where we can see the circular path, we're going to take a side view of this motion. So here's the string, there's the mass, and the circular path is like that. Okay, and we'll use a coordinate system like this. Second, draw the centripetal acceleration vector toward the center of the path. So now we can draw this as a triangle. I'll draw the coordinate system here. And we have a cable, the object, and the centripetal acceleration is in this direction. And we're always going to know an angle here, so I'll call this angle theta. Okay, that's always going to be given as part of the problem. So now we know that the centripetal acceleration is in the positive x direction. Now we're going to calculate the magnitude of the centripetal acceleration as v squared over r. Where r is equal to the length of the cable times the cosine of that angle theta. Okay, so let me draw this picture again. We have this triangle. It's a right triangle. This angle is theta. The length of the cable is L. And so the radius of the circle is this. And that is equal to the length of the cable times the cosine of that angle. Now plug this into the centripetal acceleration vector based on the direction that you have. So the way we have it drawn, this is going to be v squared over r in the positive x direction, and then 0 in the y direction. And since this is uniform circular motion, that's the total acceleration. Now that we have the acceleration, now we can draw a free body diagram. Go to Newton's second law. And we're always going to be calculating the same two things on these problems. We're going to be calculating the speed and the tension in the cable. And the reason that we're able to calculate the speed is if you think about something spinning around in a circle like this, the speed that the ball is going is going to determine the angle that it's at. So the faster this ball is spinning around this circle, the more horizontal that string is going to be. Can you imagine that? And so by giving you that angle theta, that's enough information to calculate how fast it has to be going. That angle can never get to 0. It can only get, close to 0. Getting to 0 would take infinite speed. There you know, there could be cases like it's possible to give you a speed and then have you calculate that angle theta, but I'm not going to do that in this class because it takes inverse trigonometry and we haven't really talked about that, and the required math classes don't all cover that. So I'm going to always give you that angle theta and you're going to calculate the speed. Yeah.
It takes infinite speed for the ball to be parallel to the string.
Yeah, that's right. Yeah, it does seem a little surprising, doesn't it? But it's true.
What about when you like playing with a ball on the string and that string super fast?
It's just it's never parallel. I mean, it can, at the speeds you can spin it, it can get pretty close, but it can never get there. Okay, well, let's do an example problem and see how this works. Really, these problems are always the same, you know, so with this one example problem, you can do any type of problem like this. Okay, so let's say we have a mass on a 0.25 meter long string. And let's say that this angle is 45 degrees. And let's say that the mass is 0.1 kilograms. And we want to calculate the speed that it's moving along this circular path and the tension in the cable. Bless you. Okay, so we're just going to walk through the steps. So first, we're going to take a side view of this problem. This angle is 45 degrees. The length of the string is 0.25 meters. The centripetal acceleration is toward the center of the circle, so this way. The magnitude of the centripetal acceleration is the speed squared divided by r. We don't know what v is, but we can calculate r. So r is equal to 0.25 times the cosine of 45 degrees. And so that ends up being v squared over 0.177. Now that we know the magnitude, we already knew that it was this centripetal acceleration is in the positive x direction. So the centripetal acceleration vector is v squared over 0.177 for x, 0 for y. And that's equal to the total acceleration. And now we can draw a free body diagram. There's a weight force down of 0.1 times 9.81, so 0.981 newtons down. And the cable force is the only other force, and that's parallel to the cable away from the body. And now we can go to Newton's second law. As a vector, this force is going to be T times cosine and sine of the angle theta. So this is going to be T times cosine of 45, T times the sine of 45, plus 0, negative 0.981, and this is all equal to the mass times the acceleration that we figured out. And so now we have two equations. The first one says 0.707 is equal to 0.1 over 0.177 v squared. And the y equation says 0.707 minus 0.981 is equal to 0. So now we just have to solve this system of equations. Do you see a way to start this? So what can we solve for first here? We can't start with the x equation because we have two variables in it. We can solve the y equation though for t and then plug that t value into the x equation. So the y equation says t is equal to 1.39 newtons. And now that we have that, we can combine that, substitute that into the x equation. So we have 0.707 times 1.39 is equal to 0.1 over 0.177 v squared. Now we're just, solving for v, and we get v is equal to plus or minus, after we take the square root that we have to take, 1.32, no, this is meters per second. And we want the positive because it's a speed. If I had made that angle smaller than 45 degrees, that would make it more horizontal, and then we'd get a bigger tension and a bigger speed, always. Okay, so the closer that angle is to 0, the bigger the tension and the speed are for a given amount of mass. Yeah, the smaller the angle is, the bigger the tension and the speed get, because you're just spinning it faster and faster to make it get closer to horizontal. Okay, so that's the end of circular motion. Next time we'll get into conservation laws, start talking about conservation of momentum and conservation of energy. All right, that's all.